All right, welcome back, everyone. So our second talk will be given by Matteo Parisi, who will tell us about the hypersimplex versus the Amplituhedron, signs, triangulations, and Eulerian numbers. So you have 25 minutes, please.
Thank you very much. First of all, I would like to thank you organizers for inviting me to speak at this conference. And it's a pity not to be there in person. I hope to come back soon at the NBI, which was one of the last places I've been before the pandemic. So today we'll talk about the hypersimplex versus the Amplituhedron, signs, triangulations, and Eulerian numbers, which is a joint work with Lauren Williams and Melissa Bennett. And so today we'll talk about a duality between two seemingly unrelated objects. On one side, we have the hypersimplex, which is a polytope in Rn, and it has been at the center of attentions to both mathematicians and physicists in connection to the moment map torus orbits, the theory of matroids and positroid, and also in connection to tropical geometries, cluster algebras, and in particular to the tropical Grassmannian and its positive part. Also in physics, tropical geometry has been quite relevant, for example, in string amplitudes, and then also in generalized bed joint scalar amplitudes, and also in connection to the tropical positive Grassmannian configuration space, respect to the bootstrap program and the symbol alphabet for loop amplitudes in n=4 superior mills. And on the other side, we have the Amplituhedron, which was introduced by physicists to describe the scattering amplitudes of n=4 superior mills theory. And it generalizes both polytopes and the positive Grassmannian. It is part of a more general framework called positive geometries, which has been the kind of underlying mathematical structures describing theories in many, both in particle physics and cosmology. And the philosophy is that the combinatorics and the geometries is somehow encoding the physical properties, and in particular boundaries of the geometries encode some physical principles like locality and unitarity, and triangulations of this geometry are providing different algebraic representations of the physical quantities and whose properties and symmetries might not be manifest from standard physical methods, and can also shed light on some dualities. So even if these chapters were at the center of attention of both mathematicians and physicists, there didn't seem to be any connection between them. So until some collaborators and I found some remarkable combinatorial coincidences which relates the two sides. In particular, the number of certain kind of triangulations of the m=2 Amplituhedron seems to be related to the number of maximal cones to the tropical positive Grassmannian, and also the number of pieces in which we can divide the Amplituhedron, which we call chambers, that seems to be related to the volume of the hypersimplex, both enumerated by Eulerian numbers. And embracing the philosophy of our research fields, coincidences are basically hinting most of the time something that needs to be discovered. So in our joint work with Lauren Williams and Melissa, we basically proved why this coincidence holds for in these two sides, and that the hypersimplex and the Amplituhedron are related by T-duality. And this T-duality was defined in our previous work with Lukowski and Williams, and where also the first of the two combinatorial coincidences was observed. So let me just give you an outline. So I will start with the introduction of the combinatorics of the positive Grassmannian, which serves as a tool for the talk, and introduce the two objects, the hypersimplex and the Amplituhedron. Then I will move on to define generalized triangles and the T-duality. And finally, so afterwards, I will tell how signs and Eulerian numbers comes into the story, and also how T-duality relates triangulations of the two objects. And I will end with summary and outlook. Okay, let me start with the Grassmannian. The Grassmannian GR k, n is a space of k planes in n-dimensional space, and an element V can be represented as a full rank k times n matrix C. And we can think about the Grassmannian as a space of matrices modulus their row operations. And we can use specific coordinates, which are called Plucker coordinates, denoted as p sub I, which are k times k minors of this matrix C, where I is labeling the column set used to compute the minor. And then in particular, we focus on the totally non-negative Grassmannian, also informally called the positive Grassmannian, which basically arises from the theory of total positivity by Lustig and later works by Ritz and Poznikov. And it's defined as the part of the Grassmannian where all Plucker coordinates are non-negative. And in particular, we can partition the positive Grassmannian into pieces, which we'll denote as S sub m, whose elements have Plucker coordinates which are non-vanishing pi, where I is in the set M. So And there is a very nice theorem by Poznikov in 2006, which says that these pieces are, the pieces which are non-empty are cells, which are homomorphic to an open ball. And so we have a cell decomposition of the positive Grassmannian, whose cells are called positroid cells. And the interesting fact is that there is a very nice combinatorics associated to these positroid cells. And in particular, there is a bijection between the positive Grassmannian k, n and the decorated permutation pi on the set 1 through n with k anti-exceedances, which are just permutations in which each fixed point can be designated to be either loop or co-loop. And I is said to be an anti-exceedance if pi I is less than I, or if the fixed point is a co-loop. So just give an example, like the permutation pi 2413, it's written in one line notation here, and you will use it to label a cell as pi in the Grassmannian. And there are also many other interesting combinatorial objects in bijection with these cells, like planar bicolor graphs, Lebesgue graphs, or in physics terminology on shell diagrams. And there are also others like Lie diagrams, etc. But I will use mainly permutations for today to label these cells. Okay, let me move on. So introduced by Gelfand, Gransky, McPherson, and Serganova in the context of the torus orbits in the Grassmannian, the moment map is a map from the positive Grassmannian k+1, n to Rn, and which sends one element into the weighted sum of indicator vectors E sub I, weighted with the mod square of the Fluker coordinates. And the E sub I, the indicator vectors are just sums of standard elements of the basis of Rn. The hypersimplex then is just the image of the whole positive Grassmannian gr plus k+1, n under the moment map. And it's the convex hull of all such indicator vectors E sub I. And it's a polytope of dimension n-1 inside Rn. So in the picture, I just show the example of the hypersimplex 2,4. So instead of considering the whole positive Grassmannian, we can consider the image of individual cells as pi under the moment map. And we will denote these images as gamma pi, and they're called positroid polytopes. We will use coordinates from x1 to xn to denote coordinates in Rn, and we will consider specific combinations of them, x sub ij, which are just xi plus 1 up to xj. On the other side, we have the Amplituhedron. So in this talk, I will consider the m equals to 2 Amplituhedron. So we'll see here in these definitions. And so it was introduced by Nirmal Kahneman and Trinka in 2013 in the context of scattering amplitudes. And the Amplituhedron map is a map from the positive Grassmannian k, n to another Grassmannian, this time k, k+2. So if we fix a matrix Z of size n times k+2, which has all maximal minors positive, then the Amplituhedron map sends an element C of the Grassmannian to another element C dot Z just by standard matrix multiplication. And so the Amplituhedron is then just defined as the image of the whole positive Grassmannian gr plus k, n under the momentum under the Amplituhedron map. So this is not a polytope, and in general, it's not a polytope, and it has full dimension 2k inside the Grassmannian k, k+2. So very specific cases for k+1 is an n-gon. So in the picture, I depicted a 4-gon, so n equals 4. And for k equals n-2 is just the whole positive Grassmannian. And so for k something in between, then the space is non-trivial and something worth to explore. So instead of considering the image of the whole positive Grassmannian, we can consider the image of individual positroid cell as nu under the Amplituhedron map. And we will call these images Grasstopes, and they're denoted as Z nu. So here we also use some convenient coordinates, which we call twister coordinates because are somehow related to momentum twisters. And we will denote them as angle brackets y, ij, and which is the determinant of the k+2 square matrix obtained by stacking y, an element of the Grassmannian k, k+2, with the 2 rows of the matrix Z that defined before, Zi and Zj. And we will see that the signs of these twister coordinates will be crucial to describe this geometry of the Grasstopes and the Amplituhedron on this side. Okay, now let us focus on particular positroid polytopes and Grasstopes, which are called generalized triangles. So generalized triangles, this definition is motivated by the fact that this will be the building blocks of triangulations of these spaces, and also from the physical perspective, that could be the analog of the building blocks of scattering amplitudes, which are also referred as to Yangian invariants. And the generalized triangles is full dimensional, and it's the image of positroid cells under which the moment map or the Amplituhedron map respectively is injected. So in our paper, we show that there is a bijection between generalized triangles of the amplituhedron delta k plus 1, n, and the amplituhedron, the hypersimplex, and the amplituhedron a and k, 2. And this was conjectured in our previous paper with Lukowski and Williams. And so in particular, if we consider generalized triangles of delta k plus 1, n, these generalized triangles can be denoted as gamma pi, then there is a very easy operation on the permutation pi, which we call T-duality, and which is basically just equivalent to a shift by 1. So the image of this permutation is pi hat. It's obtained by basically pi hat I is equals to pi I minus 1. And so pi hat is equal to pi n, pi 1 up to pi n minus 1. So in the picture, on the left-hand side, I have a generalized triangle, so the hypersimplex, which is just the top pyramid, and it's associated to the permutation 2, 4, 1, 3. Applying this map, we get the permutation 3, 2, 4, 1. And this is exactly a generalized triangles of the amplituhedron, which in this case is literally a triangle inside this foreground. Okay, we also gave a more explicit bijection in terms of k, n unpunctured Lebesgue tilings, and this was conjectured in a previous paper with Lukowski and Spradlin-Bolovich and myself. And the connection with Lebesgue tilings was made in our new paper, and Lebesgue tilings were defined by Hall-Poznikov and Speyer in 2015. And they're in this specific unpunctured Lebesgue tilings are just collection of non-crossing shaded polygons inside an n-gon, which can be triangulated by k triangles. So let me show the example. So in the example, we have an octagon, and we have 2 shaded polygons. One is a foregon, the other is a triangle, and we will need 3 triangles to triangulate all of them, all the shaded ones. And so it's a 3,8 unpunctured Lebesgue tiling. So in our new result is that we can actually say something more. So we can define a statistics on these unpunctured Lebesgue tilings, which means we can define some quantities like the following. So we call an arc ij compatible if it does not cross any arcs of the shaded polygons. So for example, the arc 1, 8, 1, 7, 1, 6, and 1, 3 are compatible, but 1, 5 is not compatible because it crosses the arc 3, 6 of the shaded triangle. And then for each compatible arc, we can also associate an area, which is the number of shaded triangles at the left of the arc ij. So for example, at the left of the arc 1, 3, there is nothing, so the area is 0. At the left of the arc 1, 6, there is 1 triangle, so it's 1. At the left of the arc 1, 7, there are 2 triangles, so the area is 2, and so on. So in our theorem, we can use the statistics on Lebesgue tilings to fully characterize generalized triangles. In particular, for a compatible arc of the given unpunctured Lebesgue tiling, the positary point of the generalized triangles in a hypersimplex is fully characterized by those set of inequalities that you can see on the left-hand side. Xi j minus 1 is greater or equal than the area of the compatible arc. And on the right-hand side, the T-dual generalized triangles in the amplituhedron is fully characterized by the regions where the twistor coordinates yij have signs dictated by this area in the way that it's depicted there. So now we fully characterize generalized triangles independently of their original definition as images from moment and amplituhedron map, just directly in Rn or in the Grassmannian respectively, using Lebesgue tilings. Okay, so now we saw that we could characterize generalized triangles in the amplituhedron as regions in the Grassmannian where a set of twistor coordinates have specific signs. But what about regions in the amplituhedron where all twistor coordinates have a fixed sign dictated by a sign vector sigma? So these regions that we call a sigma are denoted as called amplituhedron chambers, and we can partition the amplituhedron, of course, using these chambers. But there is a natural question: which ones are empty, which ones are non-empty? The twistor coordinates are not independent, and this is a kind of similar questions to the stratification of the Grassmannian using the matter stratification in the Grassmannian using signer of Plucker coordinates, and see which ones are which regions we can get are allowed somehow. And in order to answer this question, we went on the left-hand side, and we actually saw that there was a nice decomposition of the hypersimplex in terms of simplices, which was defined originally by Stanley in the 70s, and then by later works by Sturmfeld, Lam, and Poznikov. And this set of simplices is in bijection, is counted by Eulerian numbers, and is in bijection with this kind of permutations up there, which have a certain number of cyclic descents, k plus 1. And so without going into details, knowing these permutations with certain number of descents, we can easily define these simplices and define as a convex hull of these specific indicator vectors. So there is a nice decomposition of the hypersimplex in terms of these W simplices labeled by Eulerian numbers. So we could mimic the same story on the right-hand side, the amplituhedron. And so we define specific amplituhedron chambers where the signs of all twistor coordinates are basically defined using the statistics of our permutation W. So these are specific type of amplituhedron chambers defined using our permutation W. And the remarkable fact is that the amplituhedron can be seen as the union of such W chambers, and they're counted by Eulerian numbers. And note that most of the chambers are empty and they're not realizable, and these are exactly the ones which can be realized in the amplituhedron. And so somehow in the picture we see that on the left-hand side, the hypersimplex is subdivided in 4 simplices. On the right-hand side, this n-gon is subdivided into 4 little triangles, let's say. Okay, this is very, very nice, but we also have a further things, which is actually putting in game the T-duality, which is somehow we can think W simplices and W chambers as T-dual to each other, in the following sense that a W simplex is included in the generalized triangles gamma pi of the hypersimplex, if and only if the W chamber is included in the T-dual generalized triangle Z pi hat of the amplituhedron. And so this is somehow very important statement because it's very useful to understand the geometry of the amplituhedron in relation to the one of the hypersimplex. And it will be one of the key points to prove any statements about triangulations. Because these subdivisions, these decomposition of the amplituhedron and the hypersimplex into chambers or simplices kind of refines all possible positron triangulation that we're going to define later. So let me just talk about triangulations. As I said, considering triangulation was motivated by the paradigm of positive geometries and also the definition in terms of generalized triangles here is motivated by the fact that generalized triangles can be literally seen as building blocks also of scattering amplitudes. And so the positive triangulation is a collection of generalized triangles such that they have disjoint interiors and they cover the whole space. So it's a very easy definition. And so the theorem that we managed to prove is that actually T-duality is a bijection, and it is basically the triangulations of the hypersimplex delta k plus 1 and the amplituhedron are T-dual to each other. And this was conjecture in our previous paper by Lukowski and Williams and was proved just in this new paper. And in particular, the statement is that if we have a collection of generalized triangles gamma pi, then this is a positive triangulation of the hypersimplex k plus 1 comma n, if and only if the collection of T-dual generalized triangles at pi hat is a positive triangulation of the amplituhedron ANK2Z for all Zs. So in the picture, we can see that on the right-hand side, we already know that the amplituhedron there A412 is a foregone, and the generalized triangles, remember, were just triangles. And the a positive triangulation in this case is just a standard triangulation of a foregone into triangles, and we know there are 2 of them. And we see that each of this triangulation is T-dual to the positive triangulation and the hypersimplex, which in this case is a partition of the hypersimplex in the 2 pyramids as on the left-hand side. And these things are T-dual to each other, you can see. Of course, this is the easiest example. And in general, for example, for k plus 1, we know that the amplituhedron is an n-gon. And so we expect that there are a Catalan number of triangulations. And this is also true. And it was also known that the hypersimplex for 2 comma n has a Catalan number of positive triangulation somehow. And you can see that the situation is much more complicated, and already for k plus 2n plus 8, we have more than 6 million triangulations. And so that raises the question is about how can we classify in general triangulations? And this is still an open question, so how to classify all triangulations. However, we know some nice specific classes of triangulations, and this is will be the next slide. So the first class of triangulation that we know well is actually inspired by physics, and we know that BCFW recursions led to compute effectively scattering amplitudes. And this, inspired by this, Bao and Hein in 2019 wrote a recursion relation for how to triangulate the amplituhedron, m equals to 2 amplituhedron in the way that you see there. And in our paper, we showed with Lukowski and Williams, we showed that the hypersimplex satisfies an analogous recursion relations, and this relation is T-dual to the one in the amplituhedron. Well, now basically with our theorem that we showed in the previous slides, results of Bao and He are just an easy corollary, basically. And this recursion relation, just to make more contact, involves two types of terms. The first is one with lower n, and it's in the physics terminology could be thought as a soft theorem, as a soft factor. And in the other term is in terms of triangulation with lower n and lower k, and it's a kind of associated to the collinear limit. Okay, and another very nice class of triangulations that we can get is via the positive tropical Grassmannian, which was an object defined by Scario and Williams in 2005. I'm not going into details here because it could be too long, but the easiest way I could introduce it is by basically saying that the tropical positive Grassmannian GR k plus 1, n is the set of positive tropical Plucker vectors in R n choose k plus 1, where these Plucker vectors satisfy a kind of tropical version of the three terms Plucker identities, which is written there. So in terms of the minimum, let's say, so the sum, the product becomes the sum and the sum becomes minimum, say, in the Plucker relations that the Plucker coordinates in the Grassmannian satisfy. But anyway, so the point is that using the positive tropical Grassmannian in our previous paper with Lukowski and Williams, independently by Nima, Lam, and Spradlin in 2020, we could show that basically there is a bijection between regular positive triangulations of the hypersimplex k plus 1, n and maximal cones of this tropical positive Grassmannian. And here, regular, for who is familiar with polyhedral geometry, I just mean triangulations induced by a height vector. This height vector is the vector P, which is the positive tropical Plucker vector. Okay, so using our theorem from triangulations that we said before, then as a corollary, which means that for any maximal cone of the tropical positive Grassmannian, we can actually get a positive triangulation of the amplituhedron. And so if using just T-duality as defined before. And so these type of triangulations are much more known, and in particular, we can see that also thanks to the computations by physicists, since tropical positive Grassmannian was heavily used in the last couple of years. For example, for k equals to 3 and n equals to 9, we can get more than 30 million triangulations of the amplituhedron from the tropical positive Grassmannian. Okay, let me just have a summary of what I've said. So we saw that today there's a beautiful duality between the hypersimplex and the amplituhedron, which we call T-duality. And I must mention that this T-duality is an analog of the geometric incarnation of T-duality from string theory, which is responsible for the amplitude Wilson loop duality in n equals 4 super m Mills. And as for all dualities, both in maths and physics, we want basically to learn something of one side from another, trading complexity for simplicity. And so we could understand generalized triangles of the hypersimplex and amplituhedron in terms of unpunctured cubic tilings. We could subdivide the amplituhedron in W chambers inspired by this decomposition of the hypersimplex, which was known by Eulerian numbers. And also we could provide a bijection between triangulation of the hypersimplex and the amplituhedron, despite the hypersimplex being a polytope and the amplituhedron being a subset in the Grassmannian. And also in connection with BCFW recursions and the tropical maximal cones, and the tropical positive Grassmannian. I want to say that there is much more about T-duality in our paper in connection to Plebig graphs, which I didn't mention, and also about new cluster structures that are very interesting and very promising that we are working on also. And then I also want to mention that this was also very useful to prove open conjectures that were mostly coming from physics, like m equals to 2 cluster adjacency, which was stated by Lukowski, Spradlin, Wallach, and me in the previous paper, and also the sign flip characterization of the amplitude of the m equals to 2 amplituhedron, which was stated by Nima, Thomas, and Trenka in 2018. Also, of course, all these ideas can be, most of the ideas, let's say, can be applied to higher M, and it's very interesting to know what can happen if we do that. And we are working on that. And also we can apply these ideas to the momentum amplituhedron, so which was defined in our in paper with Lukowski and Williams. And finally, I would say that I've discussed about triangulations, but we can also think about subdivisions of these two objects, and this is in their poset, and this is connected to what's called the secondary geometry. And on the hypersimplex side, it's known that it's connected to the non-maximal cones of the tropical positive Grassmannian, and there were some conjecture on the Amplituhedron side as well in my previous paper with Lukowski and Williams, and also interesting work with Mohammadi and Monin that I've done in the last year. Finally, more conjecturally, of course, the Eulerian numbers is not the first time that they appear in physics and there is connection of scattering equations. We know that the number of solutions of scattering equation of n equals 4 superior meals, when we refine them by Helicity sector, is exactly given by Eulerian numbers. So it would be interesting to explore further connections in this regard. So let me end by a quote that says that pure mathematics and physics are becoming ever more closely connected, though their methods remain different. One may describe the situation by saying that mathematicians play a game in which they themselves invent the rules, while the physicists play a game in which the rules are provided by nature. However, as time goes on, it becomes increasingly evident that the rules which mathematicians find interesting are the same as those which nature has chosen. This seems very contemporary, but of course it was said by Dirac in the 39. So thank you very much, and please feel free to ask any questions if you have them.
Thank you. Time for questions? So I have a quick question about the connection of your triangulation to the tropical positive Grassmannian.
Yes.
Is it just a can you give this, say, the number of maximal cones here? Can you compute them independently from your method by listing all this triangulation?
Okay, you mean computing from the Amplituhedron, or
right?
Or from other
tropical Grassmannian? Just from here, does it help with literally computing this numbers?
No, I don't think it really helps, but there is actually, so there is an observation which basically the positive triangulation we define are much broader, it's a much broader class than the regular ones, right? And so the regular ones have a property which such that the kind of boundaries or the facets, let's say, of each generalized triangles are nicely matching each other. So you can also use this property to kind of further select the kind of good triangulations from the broad class of positive triangulations, and which you might say it's kind of, the number is kind of close to the number of maximal cones, but you also have kind of no regular triangulations in that way. But I also want to say that we also provided an algorithm to find positive triangulation in general in the hypersimplex, and so that transfers to the Amplituhedron, which is using the W simplices. Because literally using W simplices, you could literally understand which generalized triangles intersect each other. And because we know it's easy to deal with W simplices, and each generalized triangle is a union of W simplices, and you can literally kind of construct a compatibility graph between generalized triangles using W simplices. In that way, you can algorithmically literally compute all triangulations, positive triangulation of the hypersimplex. Then from there, going to your question, you could refine computing the good ones, and then maybe checking whether there is a height vector, but it's not so straightforward in that sense. Yeah,
I see. Okay.
Thanks.
Thank you. More questions? Okay, if not, let's thank Matteo again.
Thank you.
And then we'll move to the